So this is joint work with Theo, Benson, and CMU, my colleague Bilal, and my advisor Marco. So today I'd like to convince you that observability at scale is a hard problem, and I'll walk you through the system, Microview, that we built to address this problem. Okay, first, what are microservices? I guess most of you are familiar with this picture. So microservices is this concept for which we break down an application into many modular components, which are typically deployed as Linux containers, each with its own stack. We get fancy things like faster development, we get elastic scaling. However, the trade-off is in complexity. And the reason is that with microservices, because the fact we have many more modules and each is running on its own stack, the failure surface tend to increase, and it's way more complex to ensure the health of the application. So how do we manage that complexity in practice? The answer is observability. And specifically in our work, we focus on metrics, which is one type of observability data produced by microservices. Metrics are essentially time series that expose the application or runtime state of each microservice. So they might include things like the number of connections, if the microservice is a database, or it just can be the CPU consumption or memory usage. So if we look at production systems, the number of metrics that microservices generate is exploding. To be concrete, this is Uber. And according to their own engineering blog, their observability pipeline ingests 500 million metrics per second, 500 millions. And of those, roughly 20 million per second get persisted to long-term storage, which now, if you do the math, on an AWS managed Prometheus instance, it sums up to around $21 million per month, with 150 days of retention, which is a reasonable assumption in practice. So in this work, we take a step back and we reconsider the end-to-end workflow of metrics collection system. So in production monitoring systems, such as Prometheus, every microservice gets instrumented with dedicated observability modules. These modules, which I call metrics exporters, are in charge of reading metrics value and exposing them over the network. Then, a central collector that lives on a separate node pulls the metric values from every exporter at a fixed schedule, which is what I call the scraping interval. Now, the problem is that the collection process does not come for free. In production servers, operators typically try to keep the CPU utilization high to improve efficiency and save cost. However, because the metrics exporter and the application workload now coexist on the same node, metric collection can actually affect the application SLOs. So to quantify this, we ran a simple experiment with a front-end microservice in Kubernetes, and yellow intervals here correspond to the collection cycles. On the left side, we plot latency, and on the right side, we plot throughput in terms of number of requests per second that the front end can sustain. And we can observe that both get almost 2 times worse during the collection cycles. And while you may say one obvious solution is to collect less frequently to minimize the occurrence of these contentions. However, this creates a tension with the requirements of today's microservice applications. Debugging microservices targets very specific failure modes, such as cascaded and metastable failures, that require engineers to investigate about cause-effect relations that occur on short time scales. However, production monitors samples much more slowly. For example, Prometheus recommends engineers to scrape every 10 seconds to a minute. This example shows a concrete case of a cascaded failure involving 2 microservices. On the top left plot, we can see that the failure propagates from the payment service to the order service, and on the bottom left plot, the vice versa. While these 2 cases show different cause-effect patterns, they actually appear identical without fine-grained monitoring. So in summary, we can identify 3 requirements for an ideal metrics monitoring system. First, and by thinking to the Uber case, an ideal monitoring system should maximize storage utility. And by storage utility, I mean that a monitoring system should try to persist only those data that contain useful insights, while disregarding irrelevant and redundant data. Second, as we just said, we want fine-grained visibility. And third, we don't want the monitoring system to contend with the application workload. So over time, our community has built several methods to cope with these dimensions. One obvious method is sampling, which is the approach used by OpenTelemetry, Prometheus, and many other production monitoring systems. If we do sampling, we are essentially trading storage utility and time resolution for low overheads. Secondly, other approaches propose metric selection, such as sieve, in which to improve storage utility, we try to discard correlated metrics, which are metrics that variate with correlations. However, these approaches do not address the other two requirements. Finally, the community proposed RDMA-based collectors, like Zero, to bypass the host CPU. This type of approach can, in principle, scrape metrics at fine resolution and do not create contentions. However, it does not address the storage utility and still ship every metric to the backend. Microview, our system, is the first approach that satisfies all the three requirements simultaneously. And so with Microview, we argue that the fundamental limitation of today's monitoring systems is that intelligence is essentially centralized. And by centralized, I mean that if we look at where metrics are processed today, which is represented on the left side here, all the analysis happens offline at the collector. As a result, on this architecture, all the metrics that microservice produce are collected regardless of their significance. Instead, our idea with Microview is why not moving the intelligence close to the source, and instead of shipping every raw metric and analyzing it later, analyze them online next to the service that actually produces them. And ultimately, with Microview, our goal is to ship only this subset of data that actually matters. OK, so why does this make sense in practice, and what actually we mean for local analysis? So, well, our intuition here is that while failure attribution typically require a global centralized analysis, failure detection is actually local. For example, here on the left, we list several types of performance issues, and on the right, the corresponding metrics that would present significant variations if such issues occurs. And we can see that for a broad class of performance issues, it is actually possible to detect them online, locally, using local available metrics. And so with this in mind, the goal of Microview is to provide real-time local access to the metrics of any given microservice, and based on the metrics, detect locally anomalous conditions. Then, once anomalies are detected, Microview provides local feedback that include which performance problems have been detected and which are the metrics that show the symptoms. Finally, these feedbacks can be input to observability exporters. Exporters here include metrics exporters, as well as exporters of other observability data, such as distributed tracing, as we will show in our evaluation. And now, a natural question here is about the cost for this fine-grained access, why that should be more convenient, and how fine-grained we can achieve. And so for this, we actually have good news. We ran an experiment in a control environment, and the experiment, according to our measurements, demonstrates that the costs are actually dominated by remote ingestion and not by local access. So in this experiment, we measured the CPU consumption of a cAdvisor metrics exporter in a Kubernetes environment, and we scaled the number of containers on the x-axis. Our baseline here is when we access metrics every 10 seconds locally, and we ingest from the remote collector every 10 seconds. Now, when we reduce the local access to 1 second, we get around 2x increase in the CPU consumption. But when we reduce also the remote ingestion to 1 second, we almost hit 10x. OK, so far we made the case for local access to metrics. However, there's still one overhead that we didn't consider, and which involves processing the wealth of metrics to realize the analysis cycles that Microview envisions. So the question here becomes, can we analyze metrics locally without paying for it? And to answer this question, we first ask ourselves what are the characteristics that an ideal anomaly detector needs for microservice metrics. Our first observation is that the behavior of many microservice metrics is actually correlated. For example, for the Redis key value store, we can see a strong correlation between the cache hit rate and the number of key expiration or other similar metrics. So this leads us to our first requirement, which is using a detector that is able to capture complex correlation patterns in multivariate variables. Our second observation is that the microservice environment is actually very dynamic. For example, measurements at Meta report about 10K deployments per week. And this leads us to our second requirement, which is adaptivity. So ideally, we want our detector to require minimal operator knobs. And we have the lightweight requirement from before. So the natural family for these methods is actually dimensionality reduction, which like PCA or SVD can match the three requirements. Here we assume that metrics can be seen as a matrix that evolves over time once new samples metrics are collected for each local scraping interval. And by using PCA or SVD, we can reduce the metrics to a subspace, which essentially would be naturally able to capture multivariate pattern, and also would be able to require adaptation with minimal operator knobs, because we can always recompute the subspace. However, the fact that we need to recompute the subspace when a new metric sample is collected, it violates our lightweight requirement, because this operation is very complex. So to cope with this, we actually borrow from matrix sketching, which is an approach proposed in different community. I will skip, in the interest of time, the details here, but it's essentially a way by which we can approximate the original matrix by a smaller matrix, which we call sketch, and obtain the subspace directly from the sketch. So the nice property of this is that the sketch can be updated in streaming, so we don't have to append the new metric sample to the original metrics, but just recompute and incorporate the knowledge in the sketch itself. And by doing that, we can actually compute the reconstruction error to detect when a sample presents an anomaly. Please refer to our paper for the full mathematical details here. So in this way, we have solved our original problem, which is how do we ensure that the processing cycles do not overload the CPU of the host. And we did this through lightweight sketches. The second architectural methodology that we use is by offloading the sketch execution to infrastructure processing unit, which are more and more common in data centers. By doing that, we ensure that the sketch is isolated by user workload, and the CPU cycles are dedicated to profitable workloads such as microservices. Also, for the details of the architecture, please refer to our paper. So in our evaluation, we focus on answering the question why our architecture ensures smarter sampling decisions for our observability exporters. We have 3 case studies, and we will focus on the bias trace sampler in this talk. So bias trace sampler essentially aims at maximizing the number of distributed traces collected among the symptomatic traces. These are the traces that suffer from the performance anomalies that we discussed before. So we evaluated this across 2 workloads, and we are injecting short-lasting anomalies, shorter than 30 seconds, to assess the ability of the sketch to fire actionable insights. And we evaluate the coverage of symptomatic traces and the overheads due to the false positives. So this is our result. We compare MicroView with the baselines of head-based samplings, which are random samplers in OpenTelemetry. And we also compare MicroView without the frequent direction sketch, but instead using dimensionality reduction baselines that we said are impractical in practical settings. On the left, we observe that MicroView matches exceeds the coverage of the dimensionality reduction baselines and ensures way higher coverage than head-based sampling methods while keeping the overhead limited. And lastly, we evaluate the scalability of MicroView on the IPU cores. So for this experiment, we measured the performance on a single core on a Bluefield 2 implementation, and we observed that MicroView can actually sustain up to 256 pods with the one single IPU core. And we also compared the throughput when during the local scraping loop, when we use RDMA to access the host memory, and compare MicroView with a threshold-based approach, which is the ideal case, and with an autoencoder, which is the approach that offers best accuracy, but is impractical because it requires retraining. And we can see that the MicroView delivers 2.4 to 2.5 higher throughput than this method. So going back to our requirements, we started from identifying the requirement for fine time resolution, and we addressed this by letting MicroView access through direct memory access at sub-second granularity the metrics from the IPU to the host memory. Second, we highlighted the need for high storage utility, and MicroView ensures this by providing actionable insights to observability library. Finally, we mentioned the requirement for low host overhead, and MicroView, to address this, uses caches for streaming operations, and those caches get offloaded to the IPU to further lower down the overheads. So MicroView, it's open source and available at this link, and I thank you for your attention. I'm happy to take any questions.